Hello, everyone. I'm Daniel. I'm going to talk to you today about optimal representations for human feedback. So I'm the founder and CEO of a company called Kognic, and we're focused on how to make machine learning models solve problems that are safety critical that previously only humans could solve. So as a short introduction to myself, I've been building robots since I was a kid. I love to hack together machines and try and make them do interesting things. I've had the pleasure to spend a little bit of time both at UC Berkeley and MIT in the past. And before getting into this space, I was a mathematician and focused on collecting and analyzing large amounts of data. So before we dig in, just a brief introduction to Kognic, the company that I'm co-founder and CEO of. So Kognic provides the best data engine for ADAS and AD. So ADAS is Advanced Driver Assistance Systems, which is what we all expect in our cars today, things that make them safer and make it easier for us as a driver. So we're based out of Gothenburg, Sweden, the hometown of Volvo. We have a bit over 100 employees, and we also have another office in Munich. And we're proud to be working with companies like Bosch, Qualcomm, Volvo, and others to make their automated driving functions safer and higher performing. The problem that many of us in the machine learning community today face is that human feedback is expensive. We need humans to tell us what they expect from the machines we're developing. There was this old story about a senator in the US who was going to legislate against inappropriate material. And he was asked, how are you going to do that? What is it that you're legislating again? And he said, well, I will know it when I see it. That's a problem, because if programming can only be done by looking at things and saying if it looks right, that's going to be an expensive process. So what we're going to talk about for a little bit now is how can you leverage optimal representations to get more impact, to get each human item of feedback result in more change in your model, bigger improvements, more appropriate behavior manifested in your machine. So let's start from the very beginning. The old way of getting machines to do what we want, and sort of a very primitive form of feedback, was programming. We wrote statements, if this, then that, put in some numbers. It's one way for humans to explain what it is that we expect from machines. It's very tedious, and there's a clear upper bound to what we can achieve with traditional programming. Fortunately, a new paradigm emerged in the last, 20 years. I guess deep learning became a thing about 10, 15 years ago. And that was that we could instead program by examples. So rather than have a human be explicitly writing code, we could put together a data set and say, these are examples of what I expect my algorithm to do. And I think in this community, we're all very familiar with this, so I think we can move on. The problem with that approach is that it's very time-consuming. There are a lot of details if you have complex and complicated data. So for example, a self-driving car sees the world through a combination of LiDARs, cameras, radars. It's going to have a number of different sensors. In the example on the screen here, we see 2 LiDARs, a couple of cameras. We see all these cars around us. So for a bunch of years now, those that develop machine learning algorithms for automated driving have relied on large quantities of manually produced human judgment or feedback. Either that has been created from scratch or by somehow correcting or reviewing something that a machine learning algorithm has provided as a starting point. This is well established and well known, but it's a very low level form of programming. When I think about it, this is like assembly is to modern day programming. These are the very lowest levels of abstraction where you talk about bounding boxes and properties and sort of delineating subspaces where you say this is an object. This is going away, or rather it's getting bundled into something that is bigger. One big reason why it's going away is that if we can't figure out a way to move beyond this, we would never be able to develop the advanced sort of automated driving or even fully autonomous driving or whatever other machine learning application we can imagine, because it'd just be too much data to process. The capital expenditure, the sort of upfront investment required would just be intractable. And it's also important to remember that even if we did label everything at some point, the world is constantly changing. You're getting new sensors, new objects, new behaviors, new regulation. So there's this sort of double loop here where, first of all, you're going to be bouncing around inside, acquiring data, learning from it, defining your expected outcome, training models, and then the world is also going to change around you at the same time. So we need ways to get more leverage. We need each human feedback, sort of unit of human feedback, to have bigger impact on our model. And the first step that we took a while ago is that we've started letting humans and machines work together in this process. So just to give you a sense of sort of what has replaced the manual part in the last couple of years, a first step has been to be able to do drill down into your data sets and understand them in terms of what the model already knows and what it's uncertain about. So this constitutes sort of a data mining approach where you would focus your manual feedback, your human feedback, on those things that are hard for the machine learning model today. That's a first step to getting more leverage per unit of human feedback. It makes it possible to spend less time on things that are already obvious to your machine learning algorithm. And the most popular ways to do this is where you basically you apply a machine learning model, you sort your data set based on the loss, and you oversample the decision boundary. So whenever the model is either predicting with a low confidence or the model exhibits a large loss for something, which basically means that it hasn't been able to fully converge and sort of fit to that item in the data set, that's a candidate for more careful human inspection. Either the item in your training data set is labeled inconsistently. So one source of loss could be if there are contradictions in the ground truth on which you train. Another option is that there's an ambiguity in that object that is inherently hard also for humans. I think it's an important thing to remember here that the world doesn't lend itself to a simple ontology where everything has a well-defined type. It's an inherent part of nature that everything is sort of sampled out of a distribution. Everything comes with a probability. Some things are very likely to be what we think they are, but it's common that we're less sure. So this is one step towards getting more bang for the buck when humans look at data. And recently, there have been additional interesting things that have become available. So I think no one in the machine learning community by now is sort of unaware of the enormous impact that transformers have had and the power of the attention mechanism. So this was discovered in the natural language domain initially, but has since been applied also to visual data. So the vision transformers, or variations on this theme, are now increasingly getting or sort of showing good results on computer vision tasks. So what's interesting about this is that inherent in these models is the concept of an embedding. So I'm assuming some sort of advanced knowledge here in terms of you being familiar with the large language model concepts. So as you know, then, inside the language model, you're, during training time, finding an embedding for each token in your sentence. And the innovation that the attention paper sort of added to our understanding of this was that rather than learn a universal embedding for a word that is the same everywhere, we have learned a vector that is specifically tailored to the context in which the word occurs. So it's been sort of auto-regressively tuned to the context. And that means we're getting much more subtle vectors that make patterns appear that previously were not available to machine learning models. So these patterns are what we now see take the world by storm through things like ChatGPT and variations of that. And the secret is that you want to find the representation of each token that maximizes your ability to predict the next token in the sequence. So we're going to be inspired by that idea and look at how you can use that to increase the leverage you get when you're dealing with visual information. So in the old paradigm, we presented humans with images, ask them to draw a bounding box, assign a set of properties, a lot of clicking going on there. What we're seeing now is that we can learn embeddings that represent objects in the data, in the raw data, in order to predict the next time step. So since in the automotive domain, our customers are recording sequences for obvious reasons. You equip a car with a LiDAR, a radar, a camera, you drive for a while, you get a sequence. Rather than try and have a human craft a small crude vector, maybe saying this is a vehicle, it is a sedan, it's the color gray, it's not an emergency vehicle. People have imagined a bunch of different properties that they think make sense to label objects with. And the purpose has been to then train typically a convolutional neural net, in order to be able to recreate those object boundaries and those properties in real time while driving. Turns out, though, that the information inherent in that handcrafted little vector doesn't necessarily give you very good predictive properties. So instead, the paradigm is that you're trying to find a representation for an object, just as you do in language models, such that you can predict the next step. We believe, and I believe, that understanding your model's behavior through that latent space is inevitable. So rather than try and explicitly label things in order to, instill some behavior in the model, we're going to learn representations in order to predict the next time step. And then we can work our way back towards the visual domain during the debugging phase. So for example, maybe you've trained a driving policy to navigate some intersection, and you've learned in a semi-supervised or unsupervised way to find appropriate embeddings for all the objects around you in that scene. But your car still doesn't do quite what you expected it to do. Then it might make sense to apply human feedback to basically decode sort of the latent representation and start looking at things in terms of, I wonder what the model sort of grouped this thing with that it's seen before. So these embeddings typically become clustered where objects with similar properties find themselves close in some, lower dimensional space. So the vectors are very high dimensional. You need to do some dimensionality reduction. You can do some, TS&E, sort of principal component analysis, where you basically take the larger vectors and squeeze them down into 2D or 3D. And we're now moving to, rather than labeling objects by clicking them one by one, you can instead look at them in latent spaces. So you can query by encircling some part of your latent space and then getting the visual representation that corresponds to that. And you can see if there are objects that are unexpected, or where you think that, I probably haven't sampled enough for the unsupervised part of my model to find appropriate embeddings. And that gives you way more leverage on each item of human feedback. Instead of clicking 100 times or 1,000,000 times or 100 million times, you can instead just circle areas in latent spaces with a handful of clicks and get an immediate reflection of that in your visual galleries or whatever other method you employ. So obviously, the world in the eyes of an automated driving function is extremely complicated. So the way we are increasingly thinking about this is that creating an automated driving function is basically like curating some subspace of this learned latent space that corresponds to acceptable driving. And I know this is a little bit abstract, and there's a range of experience in the audience here, but basically, if you think of it in the language domain again, which is perhaps more accessible, you want to avoid, and I'm stealing here from Anthropic, which I think is an inspiring source of knowledge here, by the way. So this image here that I'm showing you is, if you take the latent representation inherent in a large language model, and you start sort of probing it by looking at the embeddings and the sequences that are inherent here, you can find areas that correspond to inappropriate output or hate speech. And there are a bunch of things here, as you can see. It's profanity, it's soliciting harmful advice, it's piracy, theft, substance abuse. And if you log into LinkedIn or Twitter on any given day right now, you'll see people trying to jailbreak language models. It's kind of the new fun thing that people can do to try and break the technology. This is why we can't have nice things, that sort of problem. And what Anthropic and others are trying to do now is figure out, how can we learn a policy such that we can sort of isolate areas and prohibit that output in our language model. And that gives you again, a way to gain more leverage when you apply human feedback. So rather than have to, explicitly say yes and no on a large amount of things, you let the language model learn a latent space based on all available language that you've sort of probably already tried to curate and sort of moderate. And then you can probe that space by asking carefully, selected questions, and through a much smaller amount of human feedback, identify areas here that you do not want in your model. So we, Kognic and me personally, think that the next step in terms of, the current step, to be honest, I think most advanced machine learning teams in the automated driving space has adopted this quite some time ago. But clearly, the evolution we're seeing now is where humans are asked not to operate on the sort of raw data that is recorded coming straight from the sensor, but rather some latent representation where each click can have a substantially higher impact. And this opens up for this old debate about whether it's going to be possible to provide sort of an end-to-end learned driving function, or if you're going to need some form of intermediary representation. Probably a lot of you are familiar with Comma AI and George Hotz, who has adamantly argued that end-to-end learning is the only way to go. I was, for a time, skeptical of that approach because I believe that you need to have a intermediary representation that you can analyze and debug in order to correct things and fix them. And I guess I still believe that, but I see the two concepts converge more and more, where we will probably see an end-to-end learned function, but I think we will have humans sort of look into that latent representation in order for us to get the desired behavior from the system, even if it's not explicitly making decisions the way we maybe thought it was going to do 5, 10, 15 years ago. And then if you want to get even more, again, bang for the buck here, I think it's a really exciting development where teams are now trying to learn through reinforcement learning policies for how to assign humans questions that have the maximum sort of impact on achieving whatever, if it's a moderation task or if it's a safe driving behavior thing. This sort of meta learning where the policy by which you ask a human something and then combined with operating on the latent representation, I feel like that's something that's very powerful and basically inevitable in terms of where we're going. There are also other interesting ideas and things that you can try out and take a look at. So, for example, neural radiance fields is a pretty cool new idea that could also, in some sense, be a better representation or a way to find a better representation on which for humans to apply their feedback to. So the idea is basically with neural radiance fields that you can train a neural network to be either an object in an environment or the background. And if you have a small set of images from different angles in your environment, and I still think this is somewhat mysterious, honestly, these neural radiance fields or NERFs, these neural networks, can actually, even with random initialization of the weights, learn the 3D shape of objects surprisingly well. And that means that if you have a human apply a small amount of feedback on a recording of a scene, saying, for example, how many objects are in there and roughly what is the trajectory that they're following, you can then throw a bunch of nerves onto that scenario and have them latch on to all the objects, follow them through the scene and learn their 3D shape. And then you can observe this environment from any point and angle in the space around you. There's even results that indicate that if you initiate weights in a carefully selected way here, you can carry on, sort of transfer learnings you've made from other situations. You can use, for example, ShapeNet, which is a data set of 3D shapes, such that the network can even imagine the side of the car that you maybe haven't seen in your recording. So this gives us a way to massively sort of upscale, if you will, the potentially small amount of recorded data that is available in your recording. Again, the end goal here is to give humans a way to express their opinion about what the machine learning model should do in as efficient a way possible. This is exploratory. I think there are certain challenges with this, but it's another example of what I think is going to happen in the future. Or, you know, this isn't, nerves are definitely a thing now, but the ubiquitousness, like how common they are, is going to, I think, increase a lot. So to kind of conclude my brief talk, we're strong believers in a future where humans and machines work together to do safety critical work. I'm not worried about the singularity or the emergence of some super AI that's going to take over, at least not on my good days. And I believe humans will actually be needed for setting goals for machines. But I also believe, and Kognic believes, that complex goals are best defined and achieved through iterative feedback. So we want to give humans a way to apply feedback with as much leverage as possible. Every time a human needs to manually say, I think this is good, but I don't like this, we want to have the maximum impact on the model possible, because human time is expensive. And we are building great tools at Kognic that help you achieve this so that you can get better machine learning models, develop them faster, and make more cost-efficient use of your budget. If you want to talk more about this, or if you have any questions, you can feel free to reach out to me or anyone on the team. And thank you so much for listening.